Hello everyone. Good morning. My name is Sandesh Ghimire. I am a postdoc researcher at Northeastern University, and today I'm going to talk about probability and statistics for machine learning. In this talk, the main objective is to try to introduce basic concepts in probability and statistics and make you comfortable about the notations and lay foundation for the technicalities that you will need later. I'm not trying to give you a comprehensive lecture on probability and statistics, but think of this as we're trying to peek into the vast world of probability and statistics, into machine learning through the eyes of the probability and statistics. The organization is why we need probability and statistics, and then we'll talk about basic probability and statistics, its properties of different distributions and applications, and some advanced topics which may or may not be relevant to you at the moment, but will open your eyes about the vast possibilities that lie ahead in the future. So, why do we need this topic in this winter school? Probability and statistics talks about randomness and uncertainties and how to analyze those when we try to do machine learning, for example. Different events, they have certain uncertainties and randomness associated with them. Things are not certain, and how can we study those type of phenomenon? To study those phenomena, we try to use tools from mathematics, which are covered in the topic called probability. So, for example, if you look at different physical phenomena, some of them have intrinsic uncertainty and randomness in them. For example, quantum systems, this is a Schrodinger equation, and which are inherently stochastic in nature. Things do not happen in a deterministic way as opposed to what we are familiar in day-to-day life. In such scenarios, we need a mathematical tool, for example, to study the uncertainty. And here this psi square gives us a probability density of an object in a space and time. But there are other scenarios. For example, if we want to model the climate or climate change, try to predict the climate, this may not necessarily be stochastic inherently, like a quantum system, but we are aware of things and we have limited knowledge of the things, and the things that we don't know, the factors that affect the climate change, those unknown factors, we incorporate them through distribution, and we assume that things happen with certain probability in certain ways, and try to model the system in that way. So these are two types of, broadly speaking, two types of applications where we might need to reason about how things happen and what is the probability of the things happening in real life. But this I'm talking in a more general way, in a general topic. But in this winter school, we are actually interested in machine learning and why probability is needed in there. So, for example, here, let's get directly dive into the deep learning, where we are trying to optimize some sort of loss function. This, let me try this. Whoa, this is very hard. Okay, this L is a loss function, and F is a function prediction. This could be a neural network prediction that takes in an input X and gives you a certain prediction that is y. So we say we want to minimize expectation of this loss with respect to a certain distribution p of x comma y. But what does this expectation mean, and what does the probability p x comma y mean? We need to understand these things before we get into the deep learning. If we want to do something, if we want to do something more fundamental or try to go beyond basic training of neural network, then we need to understand these stuffs. And this is the reason why we are starting with the probability and statistic on our first day. Similarly, there is a field called uncertainty in deep learning. I mean, uncertainty can be in other topics in machine learning also, but because I guess you are interested in deep learning, there is uncertainty in deep learning. A prediction with uncertainty requires you to reason about probability distribution of your predictions, and you need this type of knowledge about probability and statistics there. And another example is reinforcement learning, or where an agent interacts with the environment. It gets rewards and it does certain actions. And usually the framework of reinforcement learning, for example, is based on probabilistic modeling. You would rarely find anything that is outside that is modeled in a non-probabilistic way if you go to reinforcement learning. So, and the reason is pretty obvious, because in reinforcement learning, the scenario is like you have an agent that interacts with the environment, and when you interact with the environment does not respond in a deterministic way. So there is always certain possibility of a bunch of events and different possibilities for other events. So you need to model that with the distribution of how things will happen or unfold once you do the action. And usually, I mean, the action is also in a probabilistic nature. So these are some of the examples where probability and statistics plays a very important role, and it is basics of everything in machine learning. So let me start with the fundamental ideas. These might be too simple in the beginning and maybe a little bit hard at the end, but bear with me and try to ask questions if you have any confusion, because I believe you would be able to take a lot if you ask questions and interact. So let me start with the random variable. So what is a random variable? It could be anything. For example, the outcome of a coin toss is a random variable, and the reason why it is a random variable is because you cannot say deterministically what you will get if you toss a coin. You might get a head, you might get a tail. It is random with certain probability. So you realize that there are two components to it. One is that even if we say that something is random, we say that it has a certain events that happen with certain probability. So it's not like completely random. Like it's not like we do not have any information about what will happen. We have information. For example, we know with what probability you will get head, but you don't know what you will get once you toss next. For example, if you toss a coin, you don't know what you will get. The thing that you will know is what is the probability of the coin. I mean, you might not know that either, but we usually model by assuming that you know that. So if you denote the event of output of a coin toss as x, you can think of x equal to 0 as getting a tail in the coin toss, and x equal to 1 as getting a head, and the x is called a random variable. So other examples are like, for example, if you are playing poker, if you get the probability that you will get a flush, for example, is a random variable, because you don't know whether you will get that or not. And I talk a little bit about quantum mechanics. If you look at the position of an electron, you don't know where it is. there is a distribution over the space where you might find an electron, but you don't know where it is. It is a random variable. And okay, sorry about that. Price of stocks, for example, you might be interested in making some money, but the problem is you don't know which stock will go high tomorrow, and therefore it's a random variable, because if it were not, then we would all be very happy. So we talk about random variables, but so how do we establish this framework of probability? So we start with something called a probability, which means you assign a number that is between 0 and 1, and you say that there is certain probability to an event. So for example, in a coin toss, if the coin is unbiased, for example, there is a 50% probability that you would get a head and 50% probability that you will get a tail. So this head and tail, these are called the events, and they fall on the sample space or the event space. And this is discrete in nature. If you noted here that you need to pay attention, this is not a continuous space. You can either get x equal to 0, which is tail, or you can get x equal to 1, which is head. I mean, if you toss a coin, we would assume that it would not fall in midway or something like that, but just it's either 0 or 1. So this is a discrete space, and to each state you assign a probability, which is what is the probability that you would get a tail, and what is the probability that you would get a head. And second thing that you need to note is that the sum of these two events is equal to 1. So these are the fundamental principles based on which we develop a probability theory. The fundamental principles remain the same, but the math starts to get evolved, and you would get much more advanced things. You can do a lot of advanced things, and there is something called a measure theory, which is a rigorous mathematical framework that tries to formulate these things in a mathematical way, in a more rigorous way, so that mathematicians can work on it. But the basic principles are the same. So probability is a mapping from an event to a number between 0 and 1. This is for a discrete probability, for example, because in continuous you talk about something else. I'll talk about the continuous probability density. So this is probability. So what is statistics? So roughly speaking, statistics means you want to infer certain things about the statistical or stochastic phenomenon. For example, if you toss a coin 10 times, you get the result like this: 1 1 0 1 0 1 1 1 1 0, for example. So a natural question that you might have is, what might be the probability of head in this coin? For example, it is, I mean, the number of samples is quite low. It's just 10. I would ask you to refrain from trying to infer anything from there. But for the sake of argument, let's say we want to infer the probability of head in this coin. Like it certainly looks like a biased coin. It is more biased towards 1. So if you want to bet with your friend, you might want to use this coin and say, I would bet on head every time, so that most of the time you would get a head more than 50% of the time. So these kind of things that you want to infer a parameter of a phenomena. So if you want to infer the parameter, so I talk about phi here. Let's say the probability of getting head is phi. Then you want to estimate this phi, for example. Then that falls within the regime of statistics, and you want to understand the phenomena that explains your data. This is roughly speaking, this is what statistics is. So I talk about probability and statistics. There is something called the distribution, which means you try to describe the probability. So I said Px equal to 0 equal to 0.5, Px equal to 1 equal to 0.5, but when you try to describe more complicated things, this type of description become infeasible. Like you cannot describe everything in words like this. So and also like it's difficult to work with this type of definitions, and therefore you need some sort of mathematical framework, and that is given by the distribution. So in a distribution is a way to define what different probabilities of different events are. And depending on your input space or your event space, also called a state space, if the state space is discrete, for example in a coin toss, then you are talking about a discrete probability distribution. If the state space is continuous, for example if you want to model the probability distribution of the stock, it's not like the stock would either be $10 or $20. It might be 10.1 or 10.001, or all the continuous numbers are possible. So therefore events are continuous, and you want to model the probability of the continuous state space, and that would be a continuous probability distribution. I have been talking about the coin toss. Many people talk about coin toss because it's easy to describe. There is a distribution called Bernoulli distribution, which talks about this type of events. You have two types of events, x equal to 0 and x equal to 1, and you assign a certain probability, let's say phi, to x equal to 1 and 0 to x equal to 1 minus phi. Then there is something called a probability Bernoulli distribution, which has the parameter phi, and there's something called a probability mass function. I'll talk about probability mass function. And when you talk about the distributions, you talk about different properties. For example, I'm talking about the expectation, and I'm talking about the variance and probability mass function. So once you specify these quantities, you are fully specifying your distribution. So you no longer need to say, well, the probability of getting a head is equal to 0.4 and the probability of getting a tail is 0.6. You can still say that, but you don't need to. So once you specify this probability mass function, you have specified everything. So for example, here the probability mass function is phi to the power x 1 minus phi to the power 1 minus x. So let's say you want to find the probability of getting x equal to 1. So you just plug in x equal to 1 in this equation, you get phi to the power 1 and 1 minus phi to the power 0, and you get phi. So this statement here, p of x equal to 1, is somewhere hidden inside this probability mass function. And similarly, you can do x equal to 0, and you figure out that probability of x equal to 0 is equal to 1 minus phi. So you have also this equation is hidden here. And similarly, I will show later that you can also compute the expectation and variance all from this probability mass function. So this is a way to express the distribution in a more mathematical and a concise way. But essentially it's trying to describe the probability. So there are a couple of properties that a probability mass function must satisfy. For example, the probability of a discrete event must lie between 0 and 1, and the integral p of x, summation of p of x with all x should be equal to 1. So this requirement is, like, you can understand it in a pretty intuitive way. It means that you are sort of normalizing everything to 1. So you say the probability of a whole event is always 1. So if there are 100 possibilities, if you sum the probability of all of the possibilities, then you end up getting 1. I mean, there is no reason it should be 1. Like, you could have started with saying 10 also, but it is more, I guess it is much more convenient, so people stick with 1, and you talk about all the probability summation, it should be equal to 1, and that's how it is defined and developed. So one thing that needs to be noted here is that when you are doing this summation here, you need to take all the events that are possible, so that the probability of the everything is 1. And obviously, because these are discrete, if summation of all the things is equal to 1, none of them can be greater than 1, obviously, right? And the probability cannot be negative. So now we talk about continuous distributions. So I alluded earlier that not all events are discrete in nature. There are some continuous events, for example, stock prices, and you want to model this, you want to describe this in some sort of distribution. And the thing that you use to describe the continuous variables is called a probability density function, as opposed to probability mass function. And you need to talk about the density here, because if you look at an individual event, for example, P of x equal to A, it would essentially amount to 0, because out of all different possibilities, for example, if you look at this x-axis between minus infinity and plus infinity, if you pick one number, say 1, and you say that you would get 1, let's say you are throwing a dart from minus infinity to plus infinity, and you would ask, like, what is the probability that you would hit x equal to 1? Well, it's pretty intuitive that you might never hit it, so it's a very unlikely event. So it really doesn't make sense to talk about like a discrete probability, like talking about p of x equal to 1, for example, is maybe it's not a good idea. So what people do is they talk about density. So when you want to find a probability, you talk about an event lies between A and B. So what is the probability that an event lies between A and B, instead of talking about what is the probability of event equal to A, because that is almost equal to 0. So then we talk about density, and then you want to find this area, which is to find an event between A and B. You want to talk about this area, and you need to do some integration. You are familiar with that, because if you want to compute an area, you need to do an integration. I guess you are all well aware of that. Do you have any questions? I think there is something in the chat. Any questions so far? Okay, either I'm very good or very bad. Okay, so probability density function, it has to satisfy certain properties like before, and you might have guessed that there exists parallel between discrete random variables and continuous random variables. In discrete random variables, you had that probability lies between 0 and 1. It is obviously greater than 0. Here also the probability is greater than 0, but it's not, because we are talking about the density, it is not necessarily less than 1, because what is less than 1 is the area, not the density. So you can think of, like, for example, you can make this curve very peaky, and you can reduce the breadth here. You can still get an area equal to 1, but the density you can always make it large. So it must be true that the density is not less than 1, necessarily less than 1. So like before, the integral, before we had a summation of probability of all the events. Yeah. Okay, so all right. I hope, but I hope I can write, but I cannot. So let's look at this. What you want is the probability between A and B is the area of this area under this curve. And what you want is that this area under this curve is less than 1, not that this individual value at A is less than 1. Because if you imagine this, you want to keep the area under the curve equal to 1 because it should be 1, and then you keep reducing the breadth, for example, then you would make this curve more peakier and peakier. So for example, if you keep reducing the breadth to 0.001, then because you are multiplying the, let's say for the, yeah, so let's say that this is flat at the top, then the area of the rectangle would be equal to 1, and as you reduce the width x-axis, then the y-axis should keep increasing, right? So if the x-axis is equal to 0.001, then y-axis would be probably 1000, slightly around 1000. So the density increased to 1000, right? So obviously it is not less than 1. So I mean, it's not always less than 1 or greater than 1, but it can be. So it's not necessary that the density is upper bounded by 1. It's just that the area, when you sum up the area, it should be equal to 1. And when you talk about summing up the area, like the natural question to ask is what is this x-axis? So you should consider all the events that are possible in the x-axis. So that is how you should compute the area. So that is the probability density function. Example, Gaussian distribution. I guess you are familiar with this equation. You might have seen it a lot of times. But what it is giving you is a measure of density. And again, like if you just look at this equation and plug in some value of x, it is talking about density. If you want to talk about the probability, you need to find area. So what you do is just take a small region in the x-axis between x and x plus epsilon, and then compute the area, and that would give you the probability that event around that would happen. So you need to talk about intervals, a probability of intervals, rather than probability of points when you are talking about the continuous random variables. Are there any questions in the chat? Is anyone looking at the? Yeah, so this is the things I have already said. So now joint probability distribution. So far we talked about there is an event x, but it is not necessary that there is always one event x. There could be event x and y. So then we need to talk about what is the probability that there is both the events occur simultaneously. So for example, here I am talking about again in a discrete scenario. Let's say x is price of a stock and y is output of a coin toss. So you ask things like, what is the probability that when the price of a stock is 0.5, you would get a hit? Something like you want to talk about two events occurring simultaneously. So then you need to talk about joint probability distribution. So you say, so x can take any of value between, imagine x and y are both discrete. X can take any value between x1, x2, x3 and x4, x5, and y can take y1, y2, y3. So you ask something like, what is the probability that when y equal to y2, x equal to x4? Then you need to, that is equal to this number, whatever here it is, and that would be the probability. And similarly, when you have a continuous random variables, you have a continuous joint probability distribution, and that would be a surface. So here you were talking about y-axis denotes the probability density function, x-axis denotes the event. So this is just a curve. When you have a joint probability distribution, you are talking about two events on the x-axis. On the y-axis you have let's say x-y-axis two events. G-axis you have this surface. So you're talking about a surface which denotes the density again. So again, if you want to find the probability of a certain event around a certain point, then you need to integrate, and that time you would have to do the double integral, because your x and y axis is your event. So if you imagine if you have 3 variables, you do something similar. So a joint probability distribution can be of arbitrary dimension. For the moment, we assume that the dimension is finite. So let's say there are x1 to xn maybe variables, and then you have a density, or if it is a discrete, you talk about these boxes, these matrices and tensors and so on. You keep building these blocks that give you a joint probability distribution, which are a way of describing what is the probability of certain events happening. When we have joint probability distribution, we need to talk about something called the marginal probability. So what that means is what you have is a joint probability distribution. So you talk about things like there are 2 random variables. Let's say this is this is a die roll. For some reason the die has 3 sides, and this is another let's say card playing. Like these are 2 random variables. I'm bad at this, making this. And then let's say this x takes 1 and y takes 1. So let's say the joint probability of these 2 event is 0.32. And so we keep filling this table. We have all these numbers. So this describes a joint probability distribution. We have all the things that we want to describe what will happen, which event has what probability. But what we want to reason about, or what we want to talk about, is for some reason not a joint distribution but a marginal distribution. So let's say this is a die and this is a card, and then you say that, okay, I know that when a die rolls 1 and a card gives you 1, the probability is 0.32. But what I want to know is what is the probability of die rolling equal to it rolls into 1. I just care about the dice, and for some reason somebody gave me this probability table, but I don't care about the card at all. So just give me the probability of dice rolling equal to 1. Then what you need to do is that you just look at all the events when the dice roll equal to 1, and you look at all the cards and sum up all those probabilities. Then this is the probability that you would get a dice equal to 1, because in all those instances the dice was rolling to 1, right? So obviously you just need to sum up these rows. So each row you sum it up, you get a probability of x equal to 1, probability x equal to 2 equals 0.32, probability x equal to 3 equals 0.32, and then this is the marginal probability of x. Similarly, you reason similarly. For example, there is another person who is for some reason not interested in dice, and he wants to know about this event. So y equal to 1, 2, 3. So he would sum up along the column, and you would get these 3 probabilities: 0.4, 0.3, 0.3, and this is called the marginal probability of y. So once you have a joint distribution, you can easily obtain the marginal distributions of individual random variables. This is the discrete case. Obviously, you can imagine if it were continuous, you would have to integrate. And one last thing, this is also not by chance. This sums up to 1, because this has been designed in such a way that this is normalized, meaning that gives you a true probability of marginal distribution of x. So therefore, when you have a probability distribution, when you sum up the probability of all the events, it should sum up to 1. Therefore this is equal to 1, which also gives you a hint about a property about the joint distribution, which is this summation here. If you have a joint distribution of p of x comma y, then if you sum it up across all the variables, you should get the sum equal to 1. Another example. So this is a little bit more clear, I think. So let's say these are the rooms, and there is a certain probability of event happening here, which is given by the number of dots present in each room. So on the x, on the y, we have 2 events, y equal to 1 and y equal to 2, and we have 10 events here, I guess, for x. So if you just want to talk about the probability of y equal to 1, then you just you sum it up along this, and you sum all these dots, which is, seems like sum of all these numbers is smaller than summing up all these numbers along this x-axis, and you would get this marginal probability of y. Similarly, if you want to talk about the marginal probability of x, which is you sum up along this y-axis. So you don't care if y is equal to 1 or 2, because all you care about is what. So if let's say this is x equal to 2 here, starting from 1. So you, okay, let's say 1, 2, 3, 4, 5. Let's say you want to know probability of x equal to 5 here. Then what you are doing is, you don't care about if y equal to 1 or 2. You just sum over this, and you find all these numbers and sum it up, and you will get the probability. So this is a marginal probability of x. Something quite interesting here is this conditional probability, which is I have not introduced that yet, but which I'm coming towards. So if you look at this, the conditional probability cares about a condition. So we say, what is the probability of x given y equal to 1? So for example, here the lower box is, here y is equal to 1. So when we want to talk about this probability of x given y equal to 1, you just need to look at the dots in these boxes. You need to ignore about this. So note the difference between marginal probability of x and conditional probability of x given y equal to 1. Because in one instance you sum over all the y's, in the other instance you look at the specific instance of y. Here, if y equal to 1, if it is conditional on y equal to 1, then you are talking about only this box. But if you are talking about marginal probability of x, then you are talking about summation of these things. Okay, so I already alluded. Now if you want to talk about the marginal probability in a continuous case, obviously you just need to integrate out, which is called integrate out, because you integrate y out of this picture, and then you just get the x. So if you have a joint distribution of x and y, you integrate out y, you get the probability of x. And you integrate out x, you get probability of y. So these are the marginal distributions of x and y. And of course, I am just talking about two variables because that is easy to conceptualize, visualize, imagine. If you have d variables, for example, you can talk about the probability distribution of d random variables. Then you want to just find the probability of marginal probability of x1. Let's say this I is equal to 1. Then what this notation here is saying is that you need to integrate out everything except 1, which is obvious, right? Because you want a marginal distribution of x1. So you just leave the x1, and then you integrate out everything else. So this would look like p of x2, x3, x4, x5, p of x1, x2, x3, x4, xd, d of x2, x3, x4, x5, xd. So you just leave the x1 out. Okay, so some interesting, first of all, multivariate Gaussian, which is an example of continuous probability density function. This is the equation. I guess you are familiar with it. But interesting thing about, like, this is the equation. In the exponent we have a quadratic term. This is a quadratic term. This is usually written in this form. N means the normal distribution of x with mean mu and covariance sigma. It is also written, if you look at this big X is a random variable, so you just write random variable x follows a Gaussian distribution with the mean mu and covariance sigma. But the reason I am showing it here is first as an example of a continuous probability density function, but also that note that these px and py here are the marginal probability density of x and y. So here this is a joint distribution of x comma y. And also note that these two random variables, these two marginal distributions are also Gaussian. So Gaussian has a number of nice properties, and this is one of them. And also the conditional probability of Gaussian distribution is also Gaussian. So I talk about conditional probability briefly. If you look at here, we are talking about conditional probability in a continuous random variable case. So here we have x1, x2, and we want to find conditional probability of x2 given x1 is equal to conditional probability of x1 given x2 equal to -1. So what you do is you fix the value of x2, so which is this straight line here, and you look at how the x1 changes, or what is the probability of x1 as you fix the value of x2 to -1. And this is also Gaussian. This is the conditional probability, and this is the marginal distribution. So also notice that when you slice, so this conditional probability is like slicing. When you slice it, you notice that there is a lot of mass around which is slightly shifted on the right. So therefore this is the conditional probability whose mean is towards the right. But when you look at when you marginalize across all the values of x2, you get something that is symmetric around the middle, and therefore the marginal distribution is a Gaussian, which is whose mean is around the center. So if you try to contrast between conditional distribution and marginal distribution, you realize that one is about slicing, the other is about integrating. Now I'm going towards something called a chain rule, which is one important concept that would occur again in Bayesian framework. It is one of the fundamental things, which is pretty simple actually. So when you want to find a joint probability distribution, you can write it in. You can start with the probability of C, and then you can obtain a probability of, you can start with the A given B and C, which is a conditional distribution of B and C, and now the probability of B comma C would be probability of B given C and times probability of C. So probability of A given A comma B is equal to probability of A given B times probability of B. So something like that. If you expand this equation, it looks something like this, where you start with the x1 and then you do x1, x2 given x1 and x3 given x1, x2 and so on. So you decompose the joint into conditional probabilities of smaller and smaller conditioning. Like for example here, if you want to find a joint probability of A, B, C, you do A given B comma C, and then these two forms probability of B comma C. So this is like probability of A given B comma C probability of A given B comma C and probability of B given C times probability of C. Here is an example I constructed yesterday, so let's hope this is not too boring. So you want to, here are two discrete random variables. One is that you will reach college on time. OT equal to 0 means not on time, and OT equal to 1 means you will reach college on time, and TJ means traffic jam. So TJ equal to 0 means there is no traffic jam, and TJ equal to 1 means there is a traffic jam. On a regular day, let's say there is a 70% probability that there will be a traffic jam, and there is 30% probability that there will not be a traffic jam. And if there is a traffic jam, then you will reach on time. The probability that you will reach on time is 20%, which makes sense, right? Because if there is a traffic jam, then there is a low probability that you will reach on time. And if there is no traffic jam, then you will reach college on time with the probability of 90%, which also makes sense. So now the joint distribution is something like this. So what is the probability that there is a traffic jam and you will also reach college on time? So to do that, you just need to find the probability that there is a traffic jam, which is 0.7, times you will reach on time when there is a traffic jam. So which is a conditional distribution, which is 0.2. So therefore there is 0.14 is the probability that you will reach college on time and there is a traffic jam. So pretty intuitive example, I guess, but there is a lot of text, I guess, which might make it a little bit confusing. But this is like, if you want to find the probability that you will reach college on time as well as there is a traffic jam, then all you need to do is that you need to multiply the probability that there is a traffic jam times the probability that you will reach college on time given that there is a traffic jam. That's all, right? So this is what this chain rule is talking about. If you have P of A given A comma B, if you want to find probability A comma B, then you just need to do probability A given B times P of B. Yep.
So why is the A and the order you choose? You could have chosen different.
Yeah. Well, I mean, I assume that we know the probability that there is a traffic jam, and we know the probability that you will reach on time given there is a traffic jam. I sort of like, it seems like a sort of like causal type of things. Like we know certain probability with some probability that there is a traffic jam because this is like a base probability, and then because the traffic jam causes you to reach on time or not on time, sort of like it intuitively makes sense to talk about the probability that you will reach college on time given there is a traffic jam. But if you had gone in the other way, then what you would need to do is like you would first find the probability that you will reach on time, and then you would need to talk about probability that there is a jam given that you reached on time. And actually that is a very hard thing, and I'll come later and I'll talk about how we can answer that question through Bayes rule. So it's actually counterintuitive also if you think about it, but yeah. Okay, so properties and operations on distribution. So now I talk about some basic things. I guess you have pretty good idea, and I hope you have pretty good idea, because from now on the things are going to get a little bit more mathy and more equation-y. I don't know if that is a word, but anyway. We want to talk about expectation. So at the beginning I showed you an example how in deep learning you have a loss function and you want to minimize the expectation of the loss function with respect to some parameter of the neural network. But what is expectation? Like, what do you mean by expectation? In a very intuitive sense, expectation just means the average. So if you have a function g of x, if you want to take expectation of that with respect to random variable x, all you need to do is that you need to do the integration of g of x times p of x dx. So you do an integration. In a discrete form, you do g of x times p of x. That is expectation, and it intuitively, so if there is a random variable x, its mean is, notice that I talked about g of x, which could be any function of x. But when you talk about the mean of random variable x, you are talking about this quantity, which is x, expectation of x. because expectation of x means mean of x, and expectation of g of x means mean of g of x, not x. So try to note the difference. But when you talk about a mean of random variable, it is this expectation, which ideally, if it is a continuous random variable, you are talking about this integral. If it is a discrete random variable, you are talking about some sort of summation. If you want to find a mean of a discrete random variable, you just replace this g of x with x, and then you get x px, and you sum it over x. Geometrically, I don't know if you are familiar with this type of ideas, but it's sort of like if you put, let's say there is this type of seesaw type of thing with the fulcrum here, and you put the probability density as a mass on this bar, let's say. Then when you do this integration, let's say this is a p of x, this curve, then what you are trying to find is a point where which is the center of mass of this bar, and therefore if you put a fulcrum on that center of mass, this would become stable, like it would not go either left or right. So sort of like expectation is mean is also like this. So you're trying to find a sort of like a center of mass on the x-axis, given that the density is given by this y-axis. So this is a intuitive idea, but it means mean. But also, like, notice that how much loss of information is there when you talk about the mean. So when you talk about the mean, you are talking about just this point, whereas when you talk about distribution, you are talking about this whole curve. So bear in mind that mean, even though in a lot of instances we just talk about the mean and we try to minimize the mean when you try to train a deep neural network, but it does not have a lot of information. Like, you are missing out a lot of information, and one of those information is a variance, which is a spread of the things, and there is a lot of interest on that. One of the property that comes very handy about expectation is that it is linear. But linear in what sense? Like, linear with respect to what? So assume that your probability density function is the function f, but it is formed with the linear combination of two other functions, g and h. Then taking expectation of this f is also equivalent to, first you take expectation of this z and multiply with a, and expectation of this h multiply with b and sum it up. So what this linearity means, I mean, the math is not that hard, you can just go through it. It's just a consequence of a integral, because integral is sort of like follows linearity. But what this means is that if you have two densities g and h, and then you combine it with a and b, like ag plus bh, and then you try to find expectation, you could have done it in a different way. You could have found expectation of g and expectation of h first, and then multiply the expectation of g with a and expectation of h with b, and you would have obtained the same result. You would have still obtained the same expectation of f. That is what linearity means. Independence. So we talk about independence of random variables, which is a pretty important concept. Okay, so seems like we don't have much time. Two events are independent if the joint probability of the two events is given by the product of the marginals. So if you have x and y, and you want to talk about let's say you have a continuous random variable p of x comma y, which density is p of x comma y, then it is, if the two random variables x and y are independent, if the joint distribution is a product of the marginal. So it's like if you can write p of x comma y equal to p of x times p of y. But if you remember from the chain rule, it should be something like this. It should be p of y given x times p of x. But now we are saying that it is also equal to p of y and p of x. So something weird is going on, and that something weird implies that p of y given x should be equal to p of y, right? Because otherwise these two quantities cannot be equal. So that this means that it is another property. It is like if two random variables x and y are independent, then the conditional distribution of y with respect to x is just distribution of p of y, which is like if you know something about x, it doesn't matter. Then x and y are independent. So essentially what it means is that two random variables are independent if you don't infer anything from by knowing another random variable. Like if you toss a coin and if you play a card, the fact that you get a head on coin doesn't tell you anything about a card or the price of a stock tomorrow. So they are independent. This is this example, but it's not necessary that things are always independent like dice and a card. Like things could be connected physically, but they could be statistically independent. The only criteria of independence is that the joint product distribution is equal to the product of marginals. And sort of like if x1 x2 are independent, the joint product distribution looks something like this, which is symmetrical along all the directions. Variance, I think you are familiar with the variance, expectation of x minus mu square. It can also be written in this form, expectation of x square minus expectation of x square. Certain property, like if you multiply a random variable by a constant a, then the variance gets multiplied by a square. So it's not actually linear. And the other property is that if x and y are independent, so this is another property of independence, then if x and y are independent, then the variance of x plus y is equal to the sum of b of x plus b of y, because this quantity goes to 0. But this is not always true, because if you have two random variables that are dependent, then there exists a term that is a correlation or covariance between the x and y. So you would get something like v of x plus b of y plus a covariance term. But if x and y are independent, then the covariance term vanishes, and then you get v of x plus y equal to v of x plus b of y. Okay, I think yeah, I got notice that we need to wrap up by 12 because there is some other event. I would wrap up with this example, I think, which is the variance of the Bernoulli distribution. So by the definition, a variance of x is equal to expectation of x of x square with respect to x minus expectation of x square. For a Bernoulli distribution, we know that this quantity is equal to phi, and we need to compute this quantity, which is like, how do you compute the expectation of x square with respect to x? Is you do x square p of x equal to 1 plus, like x takes a value of 0 and 1. So when x equal to 1, you do 1 square times p of x equal to 1 plus 0 square times p of x equal to 0, and that is equal to phi, because this is equal to phi, this is 0, you get phi. So what you get here is this is equal to phi, this is equal to phi square. Therefore the variance is equal to phi minus phi square, which is phi times 1 minus phi. So at the beginning I showed you that you can actually, I told you that you can actually derive a variance of a Bernoulli distribution if you know the probability mass function, and the probability mass function we know that, and here I just did that, I showed that you can also derive the variance. Okay, so covariance is a generalization of variance to a multivariate case, and yeah, I want to skip this. Okay, I think I'd finish with um, this part. Just notice that a covariance of a random variable is a matrix. So if x is a d-dimensional matrix, if x is a d-dimensional vector, then you can think of a Gaussian distribution which has a covariance of sigma, which is a d by d dimensional matrix. Which is, when you talk about a variance, you talk about how a variable is spreading. But when you talk about the covariance, then you are talking about how individual components are related to each other. So if you have x1 and x2, then you also need to talk about how x1 is related to x2, like how much x2 varies when you vary the x1. And this forms a matrix. That's why you need a matrix to describe the covariance, but you just need a vector, I guess, to describe the variance. A correlation is defined in terms of covariance. It's just you scale the covariance with the square root of variance of individual x and y, and you get a correlation. So because it is normalizing with respect to the variance, it just tells you about the how to. It's like a normalized covariance. So if two variables are related positively, negatively, you always get this between -1 and +1. Empirical mean means you want to find the mean, you are familiar with it. A covariance, you need to compute this x minus x bar times x minus x bar transpose, which gives you a empirical covariance. Because this is a column vector and this is a row vector because it's a transpose. So you get a column by row, which is a matrix, and then you sum it over all the n. So this is a matrix of size d by d, or n, yeah, d by d. Okay, I think I would leave it here because there is another event which is going to happen. Thank you, everyone.